So as usual, it'll be 10 questions, multiple choice. I've pulled from the last, I don't know, 5 years or so, 5 or fewer years. So y'all have particular questions? Yeah. Yeah, these are hard. Well, they're not hard. Once you see them, they're okay. So an object is spinning at a constant rate and has a rotational kinetic energy. You increase its moment of inertia, and its velocity decreases by a factor of a half. What is the new kinetic energy? So on these, you have two things going on. That I have the angular momentum, L is equal to I times omega, and the kinetic energy, K is 1/2 I omega squared. And doing a couple things, it says that I'm increasing the moment of inertia, so the velocity decreases by a factor of a half. So if this goes down by half, that means that I've done what to my moment of inertia? I've not halved it, but I mean, if I have this, in order for this to remain constant, that means that I has to have been doubled, right? So I've doubled I. So now it's asking, what is the new kinetic energy? Well, so those same things are going to happen over here. I'll double my I, and I'll have my angular velocity. So it's a factor of 2 there, and a factor of 1/4 there. So I have a 2 times a 1/4, which means that I'm having my kinetic energy. So B is the right answer. Right. On all those, if you see one like that, you have to look at the angular momentum and at the kinetic energy. And I would do it like that, where you write out the equations for both, and then just start. Okay, if my velocity is decreasing by a factor of a half, then what does that mean for my moment of inertia? Or vice versa, if I say the moment of inertia increases or decreases, how does that affect your velocity? And then you can look at your kinetic energy and see how it's affected, remembering that that omega term is squared. There are usually variations of that question on exams. Let's see if there's another one. I don't see any right here, but usually there are variations of that. Okay. Other particular questions? We can look at that if y'all want. You want me to find another one like that? Okay. Maya? Fall 22, number 14. Oh, number 14, you said? This one? Okay, I'm not going to get to that. That's going to be chapter 9. So yeah, we'll see that with chapter 9. I think that all the questions for chapter 8 are on exams 4. I rarely get to that for exam 3. So, but just check that guide. Emily? Mm-hmm. Is it this one right here? Yeah. Okay, so you have 3 particles, but notice that one of these particles is on the axis of rotation. So R for this particle is equal to 0. And R for both of these particles is equal to 4. Okay? So because this one's 0, you don't include that one at all. It doesn't contribute to the moment of inertia at all. But these other two do. But don't use the 8 meters because you're bisecting that equilateral triangle. Okay? 15. Okay. Okay. So here I have a bar that has a certain moment of inertia that's expanding into a disk. This is a conservation of momentum question. So Li is equal to Lf. I initial omega initial is equal to I final omega final. And I'm looking for the rotational speed of the disk. That means I'm looking for this quantity. What is omega f? So let's go about determining all those quantities. I initial that's for a bar. Let me just pull up that equation sheet to show you. So y'all probably know what it is by now. Do you know those various equations? Very good. Yes, 1/12 mv squared. But it is on that equation sheet. So just you'll have that. It'll be, by the way, you'll get the full one this time, and it'll be on the back of the bubble form. So you won't just get a part of it. There's just a lot on there. So it's the bar right here, this 1/12 mv squared. So that's going to be 1/12 mv squared. Remember, b is that length. So it's going to be 1/12 of m, which was 6 kilograms, times 2 meters squared. 6 times 4, that's 2. So I initial is 2 kilogram meters squared. Omega initial is 3 revolutions per second. You do not need to convert that to radians per second. I final, I for this is for a cylinder. A disc is just a flat cylinder, so that's this one. I've seen several students, by the way, who mistakenly said that that disc is this one. I know that they look similar, right? They're circles, but the hoop doesn't have mass in the middle, right? It's a hoop. It's not a cylinder. It's not a disc. So just make sure that you're clear on that. I've seen that a number of times in my office, that students are confusing the disc for the hoop or the wheel. They're not the same. The disc is solid in the middle, and that's a cylinder. It's just a flat cylinder. So that's 1/2 mr squared. 1/2 of the mass, which is 6, times the radius. Be careful, the radius here is half the diameter, so it's 1 meter squared, so that's equal to 3. So I get a 3 for I final, and then omega final. I just solved that for omega final. 6 is equal to 3 omega f. Divide both sides by 3. I get the answer is A2. Okay? Yeah. Other particular questions, Lillian? On the same one? Okay, so she moves her arms out away from her. So what's happening as she moves from this situation to this, she has really long arms. She's like in one of those movies, like a horror movie. So what happens there is that the moment of inertia goes up, and since L is equal to I omega, if this goes up, that means that has to go down. So yeah, when she throws her arms out, she speeds up. When she pulls them, when she throws her arms out, she slows down. When she pulls them in, that's when she spins faster. So if she moves her arms out away from her body, it's not 1, it is 2. Her moment of inertia doesn't decrease, her moment of inertia actually increases, so it's not that one. And look, it's not this either. Her angular momentum will always be constant. So in this case, it's 2 only. I have variations of that problem. So different things I could word it in different ways. And so look for those different variations on that. Yeah, of course. Okay, yeah, I was going to do it because this one's similar to that first one that you asked. These are probably the hardest of all of them, just thinking about these things. So 2 discs, A and B, have the same momentum. The radius of disk A is twice the radius of disk B. I always find it useful to draw a picture if I'm not getting the values here, so that'll help you to think about it better. The radius of disk A is twice the radius of disk B. So this is radius, this is A, and this is B. A is bigger. They have the same momentum. Here, this is, if this is R, this is 2R. The angular speed of disk A is omega. What is the angular speed of disk B? It says that they have the same momentum. So the momentum here of A is equal to the momentum of B. IA omega A equals IB omega B. I'm just going to call disk A has angular momentum omega. That's what I said up here, that the angular speed of A is omega. So is disk B, first of all, is it going to be going faster or slower than disk A? What is it? I'm going to say it again. You were right. Faster, right. It's like the dancer or ice skater that pulls her arms in. She gets a smaller moment of inertia, so she's going to be going faster. So I can go ahead and get rid of these. And then I want to ask, by how much is she going faster? I know that the radius of disk A is twice that of disk B. How is the moment of inertia dependent upon the radius? Is it linear or quadratic? Quadratic. So I is equal to 1/2 mr squared. So since the radius is twice, that means the moment of inertia is 4 times. That means that disk A is going to be going, or excuse me, disk B is going to be going 4 times as fast as disk A. All right? Whew. That's a difficult question. Not on the quiz, but y'all see me winking? That's a wink. Not on the quiz, but difficult question. You might see something similar to that on the exam. All right. All right. What else? Y'all, particular questions that you have? Yeah, of course. Mm-hmm. Hoop has a radius of 4 meters, mass 20 kilograms. I want to know the total energy of this hoop. So it's rolling at a speed of 2 meters per second, and it's traveling at a speed of 2 meters per second, and it's also rotating. Right? So it has two different things going on. It has a rotational energy and a translational energy. So the total energy will be the translational energy, that's 1/2 mv squared, plus the rotational energy, 1/2 I omega squared. And then it's a matter of getting all those things sorted out. So 1/2, the mass is 20 kilograms. The speed is 2 meters per second squared. It's given there and there. And then I need to do a little work. So I, for a hoop, that's equal to mr squared. Just remind you, go over to that table. This is the hoop, mr squared. That's equal to mr squared, 20 times 4 squared. That's 20 times 16, or 320. So 1/2 of 320. Now I also need to find omega. Remember that V is equal to omega R. That is from chapter 7, but it is on your equation sheet. It's right here if you forget. But be careful about that. Keep a check on your units. You will see a problem similar to this. It might be this one. I don't remember. I mean, the two classes have different quizzes, so one of you might have this one. I don't remember. Anyway, watch the units. If it says meters per second, I know that's V. If it's revolutions or radians per second, I know that is, well, it would just be radians per second. If it's radians per second, then I know that's omega. So I need to figure out what omega is. Omega is equal to V over R. That's 2 meters per second divided by the radius, which is 4. So that's equal to 0.5, or 1/2. So that goes up here, 0.5 meters per second squared. And now I can do this. That's 10 times 4, that's 40, plus 180, or no, 160 times a fourth, that's also 40. So the answer is C, 80 joules. Alrighty? Good question. You have to find both of the energies. FYI, not on the quiz tomorrow, but on your upcoming exam, that I'm going to give you a problem where somebody takes something and throws it up into the air, and it goes up to some height. In that case, it would be similar to this, where I would have the rotational energy, 1/2 I omega squared, plus the gravitational potential energy, mgh. Right? Not for the quiz tomorrow, but for the exam coming up in a couple of weeks after Thanksgiving. We'll come back to that. That's not important for today. All right. What else? Particular questions, or I can just scroll through if y'all. Any other particular? Yeah, Ian. Yeah. 'Cause 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 well, that was when I had 2 exams. Is this it right here? Yeah. Okay. Pretty sure I put these on there. Most exams have them. It's an equilibrium problem where I want to know what is the force. On these, you can go about balancing all the torques, like saying these are clockwise torques and these are counterclockwise torques. But on this one, if I just want to know the force, I can just say that the one torque has to equal the other torque. And then I can just get rid of all the plus and minuses. I can just say that the torque due to this force has to equal the torque due to that force. That force, by the way, is the weight of the block, which is 2 times g, or 2 times 10, which is 20 newtons. So you will have to find the force that's exerted by that mass. So I have the torque on, I'll call this torque 1, has to equal to torque 2. That's F times the moment arm, which is 4 meters, has to equal to 20 newtons times the moment arm, which is R. That's what we're, no, I'm sorry. It's not what we're looking for, we know that. 2 meters. So that's F is equal to 40 divided by 4, or 10 newtons. A is the right answer there. Variations on that, most exams, so be prepared for that. 98% certain that something's on that. All right. Other particular questions? Yeah. Oh. Well, you like these, don't you? Okay. They're tricky. So 2 discs have the same momentum. However, disk A has more energy than disk B. So how do their angular speeds compare? They have the same momentum. That means that the product of I and omega is the same for both, but one of them has more energy. The one with more energy has a higher what? A higher moment of inertia or a higher speed? Speed, right. The reason is that the kinetic energy is equal to 1/2 I omega squared. And so if the speed is bigger, then that affects the kinetic energy more. So these 2 disks, the one with the higher speed has the bigger energy. Let's see, so disk A has more energy, so A is the right answer. We can do 16. Yeah. So this is a angular momentum, conservation momentum. This is sort of like the ballerina problem where she moves her arms out or something changes shape, the bar that goes into a disc, except it's different in that there are 2 objects that are coming together. So if you have 2 objects, you're going to approach it in a similar way, but instead you're going to say that L1 plus L2, that would be the moment of inertia of the bar, or excuse me, the momentum of the bar and the momentum of the flywheel is equal to L final, or I'll call it L3. So I'll call this L1, L2, and then the both of them together I'll call L3. The bar, the flywheel, and then the final together. So the way that's going to look is the moment of inertia of the bar times omega. I'll call that I1 omega 1 plus I2 omega 2 is equal to I1 plus I2 times omega, well, I'm going to call this omega 3. I1 plus I2, it's the same, it really is the same as that free response that we had on the last exam with the perfectly inelastic collision. Those 2 objects collided and then they moved off together, they stuck together. Same exact problem, except now it's rotating. So I have I1, which is 8, times omega 1, which is 2, plus I2, which is 16, times omega 2, which is 4. Let's be careful with our signs. Notice that this is counterclockwise, so that means that 4 is negative, or excuse me, the 2 is positive, the 4 is clockwise, so it's negative. And then I add these together, 8 plus 16 times omega 3. And omega 3 is the final velocity of both of them after they've engaged together. That's 16 minus 64 divided by 8 plus 16, which is 24, omega 3. What's 16 minus 64? I think I wrote a calculator. Anybody know? Huh? Oh yeah, negative 48. So it's 48 divided by 24, or negative 2. So that's 2 revolutions per second clockwise. I know it's clockwise because it comes out negative. Okay? Is that clear? Okay. Those are a little more involved, but they're still really similar to the other conservation momentum problems that we've seen. Alrighty? Yeah. Yeah. Okay. Yeah, so this one right here, the merry-go-round. Yeah. So I have a merry-go-round. It has a certain moment of inertia. It's a disk, 1/2 mr squared. So its moment of inertia is equal to 1/2 of 200 times 1 squared. Oh, yeah, okay. Well, that's even easier. So the moment of inertia of that is equal to 200. Thank you, Lindsay. And then a kid comes and jumps onto it, as kids want to do, and I want to know what is the moment of inertia now. That kid, we're going to treat like a particle. Remember I said when the axis of rotation is outside of the body, then you always treat that like a particle. That's true here. And so that kid we treat like a particle. We can find his moment of inertia, or her, I guess, is equal to mr squared. That's going to be 50 times 1 squared, which is 50 kilogram meters squared. And now the total moment of inertia is just the sum of those two, which is 200 plus 50, or 250. Whenever I have two bodies come together, I always just add their moments of inertia, just like we do with two bodies of mass. If two bodies of mass come together, I just add their masses together. Scalar quantity just adds like numbers. Yeah, Emily? Yeah, of course. And you're going to see at least 2 of those. Okay, you'll see one like this one, where you're ranking the moments of inertia. We've done several in class. So on these, what you're looking for is the ones with the bigger moments of inertia are the ones with mass further away from the axis of rotation. So in this one, this object rotates in the plane of the page, like a wheel sort of that rotates in the plane of the page, but about different axes. Notice here I'm looking for smallest to greatest moment of inertia. So the one with the smallest is where the one that has the least mass at big radii. That would be D. You can probably tell because most of these are D already, so you sort of think that's probably going to be the case. But it's going to be D, so I can get rid of C and E. That has the smallest moment of inertia because look, at any point, it only goes out to that far, whereas all those others, you have mass that's at big radii. Now, we can also recognize here that A is equal to B, right? Those are the same. They're symmetrical. So I can get rid of this one, and well, that's it. And so now I need to know, are A and B bigger or smaller than C? Notice that with C, if I go out to big radius right here, there's no mass out here. However, if I go to A, and I go out to a big radius, I have all this mass out here. So the moments of inertia for A and B are bigger than the moment of inertia of C. Let's do another one, okay? Okay. Definitely going to see one like this. Oh, I was doing it wrong. It's messing me up, the smallest to greatest. Yeah, it is B. The answer is B. And that's what the answer key says. I'm sorry, I was getting my orders mixed up. A and B are the biggest moments of inertia because they have the most mass at big radii. Be careful with that. Sometimes it's smallest to greatest, sometimes it's greatest to smallest. I'm sorry for that. It's this. It's just fun. Let's do another one though. Oh, here's one. We might have done this one in class. You want to find first which one has the biggest moment of inertia? Or here I'm going from least to greatest. Well, I see two right here that are the same. Which ones are they? B and C are both the same. So that gets rid of this one and this one. And I also see here that B and C, that both of these have a bar that's along the axis of rotation. That means that that bar does not contribute to the moment of inertia at all, whereas that's not true for A or D. So I can say that B and C are both the smallest. So now I want to know which is bigger. Is A bigger or is D bigger? Well, notice that A has all of this mass out at big radii. And that's not true for D. That at D, I don't have all the same mass like I do on A out at big radii. So A is the biggest of all of those. So B is the right answer. Is that right? Yeah. B is the right answer. Let's rank some torques too, okay? Okay. Thank you. 19 on fall 21. Can we do this star problem? We'll go do that one too. But let's do this one too. So here, which two are the same? B and D, they're symmetrical. So I can get rid of some of these. I get rid of that one and that one. And then which one is the smallest? A would be the smallest. So that gets me the answer. I can get rid of that one and that one. So A is less than C. Oh, no, that's not right. Yeah, that's right. A is less than C is less than B, which is equal to D. You said 19 on what? Okay, so remember on these, see three things with torque: F, R, and the angle. So here, kind of like with the others, I'm going to look for some that are equal. Notice these two, one of them has a big force and a little moment arm, and this one has a little force and a big moment arm. So that's going to give us, and for both of those, the angle theta is 90. So those are going to both be the same. C and D are the same. Whoop, that gets rid of everything. But I could go ahead and rank the rest of them. C and D are the same. Are they bigger or smaller than B? They are bigger, yes, bigger, because here I have a small force and a small moment arm. So I have C equal to D, which is bigger than B, which is bigger than A. A is the smallest because it's a small force, a small moment arm, and it's at an angle. So not all of the force is actually providing a torque, only a portion or a component of that force. Let's see, they're on every exam, so let's take a look here. What about these? This is fall 22, number 7. Here I'm just asking which has the largest and which has the least. So I'm looking for the biggest force at the biggest moment arm with no angle. Which one would those be? It's 3 is the largest, right? Because it's the one that is farthest out. Looks like all the forces are the same, but it's the one with the angle closest to 90. So notice 1 and 2, they have a bigger angle. So less of the force actually provides the torque. So 3 is the largest. That gets rid of C and D. And then either 2 or 4 has the least. It would be 4, right? 4 has a double whammy, has a little bitty moment arm, and it has that angle out. So not all of the force is providing the torque. So 3 is the greatest, 4 has the least. Alrighty. Well, this is an easy moment of inertia. What's the biggest? D, and then C, and then B, and then A. Yeah, so you really just follow along since it's sort of long and linear. So D is the biggest, followed by C, followed by B, followed by A. So B is the right answer. All right, you're going to have some where you're calculating moment of inertia for a system of particles. Remember, that's just mr squared. Just do that for each particle and then add them up. Other particular questions, y'all? Yeah, of course. Okay, you're going to see ones like this where you have to find the net torque and then the angular acceleration. There are variations on this. The net torque here, oh, this one's easy because there's only one force that causes a torque. This one doesn't cause a torque because the angle is 0 and the sine of 0 is 0. This one doesn't cause a torque because r is equal to 0. Fr sine theta then would be equal to 0. So I only have 2 times 3. So my torque is equal to 2 newtons times 3 meters times the sine of 90. Sine of 90 is 1. That is a clockwise torque, so it is negative. So it's negative 6 Newton meters. So the negative becomes unnecessary in this problem because I'm just asking for the magnitude of it. Then I also need to find the moment of inertia. I, like I said earlier, is 1/12 mb squared. Just look on my table and get that for a bar, or rod, I think it's called. So that's going to be 1/12 of 2 times 6 squared. It's 2 times 72, that's 6, I think. Yeah, 6. So then I find alpha. So I find torque equals I times alpha. So alpha is torque over the moment of inertia. That's same as F over m, except in this rotational frame. And then so the torque is negative 6 over 6, so it's equal to negative 1. But again, I'm just looking for the magnitude there. So it's 1 radian per second squared. Definitely going to have one of those. Actually, probably going to have, I don't think I did it on both quizzes, but probably going to have a series of questions. 2 questions. One where you're asking the net torque, and then the other where you're asking the angular acceleration. All right. When y'all study for the quiz, do you try to work every question, or do you just try to master the individual categories of questions? What are you trying to do? Huh? You do everything? Yeah. Okay. Yeah. Sure. 4 from 2019. What's this one? Okay, so this is similar to what we had with the, what was that? I think it was like a bar and a disc or something that came together. Had these 2 objects coming together. I just want to know what is their total moments of inertia. So I calculate the moment of inertia of one of the objects, and then the moment of inertia of the second object, and I just add those things together. This is for a solid sphere and a hollow sphere. Let's just look at our equation sheet. The solid sphere is 2/5, I think that is. Yeah, the solid sphere is 2/5, and the thin wall sphere is 2/3. So I is equal to 2/5 mr squared, and I is equal to 2/3 mr squared. I tell you that they have the same radius and mass, so it makes it a little easier. It's 2/5 of 500 times 5 squared, and 2/3 of 500 times 5 squared. 1,200 plus 25. Huh? Oh, gosh. And you're good. Thank you. Sorry, the second time you corrected me. Correctly, you should correct me. Sorry, yeah, so it's a little more work we need to do. A solid sphere, which is the 2/5, right? I of the solid sphere is 500, and then that's equal to 2/5 mr squared. And here you have to solve for the mass. Okay, so I know the radius 500 equals 2/5 of the mass times the radius, which is 5 squared. Those cancels with that, 10. So m is equal to 500 divided by 10, or 50 kilograms. Now I use that to find the moment of inertia of the thin wall sphere, which is 2/3 times 50 times the radius, which is 5 squared. 2,500 divided by 3. It's about 800-ish, right? So you got about 850, just rounding, we get 800. C should be the right answer, right? C is the right answer. What is the right answer? Oh, right, 800 plus 500. Gosh, don't ask me to do math after 3. Right, 300. So I do 800 plus the 500 is equal to 1,300. Okay? Anything else, y'all? Feel comfortable with this quiz tomorrow? Yeah. All right.